This is 3 videos series on single diode mixer design and optimization using AWR Microwave Office. In this video, we are going to simulate the mixer circuit and optimize the output spectrum by changing parameters, and at the end we are going to design the RF filter to remove all the extra frequencies or spurs. So let's get started. In the first step, we are going to download the demo project using the link given in the description. Then run AWR design environment from start menu. Let's open the project first. So I have saved that on desktop. Go to diode mixer folder, and from there you will find this single diode mixer.emp file. Let's click on open button. So as you can see, till here we have designed this mixer circuit, and next we are going to run the harmonic balance simulation. To run the simulation, we are going to create a new graph, and that we can easily do by clicking over this add new graph button. I'm going to name it IF out because this is the intermediate frequency output from the mixer. Make sure you have selected the rectangular plot and click over create button. Next we are going to add the measurements. So right click on the plot and click on add new measurements. This time the measurements will be non-linear. So we'll just go to non-linear tab, and from here we have to select the power. And then we have to select the power harmonics, which is here. Data source should be mixer, and the harmonics we are going to calculate on port 2, which is the output port of the mixer. Here we go. And make sure you have selected the dBm here and click on OK. Now just I want to verify the frequency. So just go to the option of your mixer schematic, and here as you can see the single point frequency should be 4.25 because this is the project frequency. So this is fine. You just cancel that and run the analysis. All right. So as you can see, this is our IF output spectrum, and here we have a lot of extra frequencies, as you can see, because as of now we are not using any attenuators or filters in the design. So I just want to show you what will happen if we change the power of the local oscillator. So as of now the PLO is 0 dBm. If we'll go back to your mixer circuit, here you can clearly see PLO is equal to 0, which is assigned to the local oscillator power, right? So if I'll go back to our IF output plot, first I'm just going to adjust the parameters. So go to options, go to axis. So I want to optimize the left axis, and it is set to -100. So instead of going for auto limit, I'm just going to uncheck that, and let's put the parameter, let's say 100, and make this +20. Click on apply and OK. Now I'm going to add the marker at the output frequency. So if you remember from the previous discussion, the target or the desired output frequency of mixer should be 0.5 gigahertz, right? So I'll just right click, add marker, and this is our 0.5 gigahertz output frequency, right? So apart from that, we are also getting a lot of strong signals, which we can easily remove by adding band pass filter. So that we'll see later. Next, I'm just going to add a tuner on the LO power. So we can clearly see the effect of LO power on the mixer output. So let's click over this tune button, add tuner, go back to IF out, click over this tuner. Now I'm going to remove this L quad. It's not required. Let's make it 0 to, let's say 5 or 10 dBm, right? So as you can see, as I'm changing the LO power, you can just look at this marker. The output power of the mixer is increasing, all right, which totally makes sense. So as we are increasing the LO power, the output power is increasing. Next, I'm going to design a band pass filter, which we'll use on our mixer circuit and see the effect of that on the spectrum. Next, we are going to design the filter for the IF output to remove all the extra frequencies or spurs and keep the signal, which is at 0.5 gigahertz. Now to design that IF filter, we are going to use an open source tool, which is RFSim99, that you can easily find inside the same folder I've shared with you. So if we'll go to the folder, and there you'll find this RFSim99 standalone. Here you will find this rfsim99.exe file. Just double click on that. Now to design a filter, we'll just simply go to tools, click on design, filters, and here make sure you have selected the Chebyshev filter, which will be a band pass. So let's select the band pass topology. First branch will be in series. Everything else will be same. The center frequency we want should be 500 megahertz or 0.5 gigahertz. The bandwidth of the filter should be 10 megahertz, and we'll just leave everything else as it is and click on calculate. So from this tool, we got all these inductor and capacitance values. So I'm going to design the exactly same filter on our AWR design environment. So go back to AWR. Just close this tuner, go to your project panel, and I'm going to create another schematic. Let's name it IF filter and click on create button. Now to place all the components, we'll simply go back to elements, and these are all the lumped elements. And so first we'll start with placing inductor. So let's go back to inductor. We have to place the closed form of inductor. Select it. Drag and drop here. Then we'll need capacitor. So I'll go to closed form of capacitor, drag and drop on schematic canvas, and then we'll just copy paste. So one capacitor here, there will be another inductor. So you can clearly see the schematic which we are designing here, and then we'll have another inductor like that and a capacitor at the output. And then I'm going to quickly assign all the values. So this inductor will be 82.09 nanohenry. This capacitor will be 1.234 picofarad. Similarly, this will be 36.523 picofarad. Then we have this parallel inductor, 2.774 nanohenry, will be precise here, and this will be 82.091, which is same as here, nanohenry. And then we'll have the capacitor 1.234 picofarad. Next, I'm just going to make the connection here. So let's connect all these components together. I'm just going to shift it. There we go. And then this will be ground. So I'm just going to add the ground port here. And then I'm going to add 2 ports at the input and output of the filter. Just rotate it by right click. Here we go. So here we have added the filter. Now I'm just going to verify the filter by adding a graph and simulate it for S11 and S21, and we'll see what is happening exactly at 0.5 gigahertz. All right. To do that, we'll just simply add new graph. Let's name it filter S parameters. It should be rectangular plot. Click on create, and next we are going to add the measurement, which will be our linear measurement. So we'll just go to linear, port parameters, S parameters, source will be IF filter. So first we'll plot for S11, we'll just add that, and then we'll plot for S21 and add this one as well and close. And next I'm just going to run the simulation. Now before running the simulation, as you can see, I'm getting just some garbage value. I just want to add the frequencies. So let's go back to the schematic, which is our IF filter. Right click, go to options. Here I'm just going to add the sweep frequency, which will be start from, let's say, 0 to 1 gigahertz, and step size, let's keep it 0.01. Apply. So we'll have 101 points. Click on OK and rerun the analysis. Here we go. Now here we have to adjust since you can see the amplitude is going up to -800, which we don't want here. So I'll just go to options, go to access, left, remove the auto limit. Let's make it -100, and the maximum value can go up to, let's say, 20. Apply and OK. So as you can clearly see, the return loss at 0.5 gigahertz is minimum. All right. So as you can see, and all other frequencies, you can see this band, all the other frequency will be rejected except this band of between. I'm just going to add marker here so we can clearly see. So this band will be approx 450 megahertz to, just move it here, 553.8 megahertz, right? And the center frequency will be 500 megahertz. So if I'll add another marker on this return loss parameter, you can clearly see it's at 500 megahertz. It is minimum, which is approx 60 dB. So there will be approximately negligible return loss at this frequency. That means all the signal will be passed from port 1 to port 2. So we are going to implement this filter to our mixer circuit. So let's go back to our mixer circuit. Let's make some space after diode biasing. Just going to shift it a bit toward left side. Make some space here, delete this, and I'm going to add another sub-circuit which will be our IF filter. Okay, connect it like that. Now go back to our IF output spectrum. Here we go. And now I'm going to run the analysis again and close it. Here we go. So as you can clearly see, we have removed all the extra frequencies, right? So you can simply compare the plot with and without filter, and you can clearly see the band pass filter we have added is able to pass 500 megahertz frequency and rejecting all other frequencies. So this is the desired output we want. Amplitude we can simply increase by adding amplifiers, or you can increase the LO and RF power of the mixer. So you can simply play with these values and you can plot for different spectrums, and you can also try different filters at the output of the mixer. Similarly, you can plot for different LO powers and RF power and run the different sweeps to plot for SFDR, phase shift and other measurements. So hope you can design and customize diode mixer for your mixer design requirements using AWR Microwave Office. For more tutorials, visit us at resources.emaeda.com and don't forget to like and subscribe our YouTube channel.